What if one element disappeared and every living thing vanished instantly? That element is carbon, the atom inside your DNA, your food, and every cell of your body.
Imagine waking up tomorrow to an impossible reality. You look out your window and every single tree has simply vanished.
Oh, wow. Okay. Dark start.
Right, but the grass is gone too. Every bird, every fish, every insect, every human, just, gone.
So just a completely sterile rock floating in space.
Exactly. But the erasure doesn't even stop with living things. You look around your room, and there is no plastic anywhere. The clothes in your closet have vaporized.
Which is basically everything in a modern room, yeah.
Books, medicines, the fuel in your car, all gone. Even the diamonds in your jewelry box have just ceased to exist.
I mean, it sounds like an apocalyptic sci-fi movie.
It really does. And most terrifying of all, the very DNA that serves as the instruction manual for every living organism on Earth has completely disappeared.
Yeah, that paints a picture of a sudden just total erasure of the world as we know it. Unrecognizable.
But here is the wild part. All of those seemingly unrelated things, from a 300-foot redwood tree to a diamond ring, from the plastic casing of your phone to the DNA inside your own cells, they all depend entirely on one single extraordinary element.
Element number 6 on the periodic table.
Yes. Carbon.
It's an atom so remarkably common that it exists in every single cell of your body, and yet, its chemical nature is so highly specific that biology and life as we understand it simply could never have evolved without it.
Welcome to today's deep dive. Our mission today is to uncover the truly unbelievable story of carbon. We've got a ton of great source material today, and we're going to explore why scientists universally call it the element of life, right?
Right, and how it quietly dictates almost every aspect of our modern civilization.
Exactly, and why every single atom of it inside your body is actually billions of years old. Okay, let's unpack this. Because before we can talk about what carbon is doing here on Earth, we actually have to rewind the clock to a time before Earth even existed.
Yeah, if we go all the way back to the very early universe, carbon just wasn't around.
Wait, really? It wasn't there at the start?
No, not at all. The cosmos was essentially just a massive, expanding cloud of hydrogen and helium.
Yeah.
Those are the simplest, lightest elements in existence, just 1 or 2 protons. And for a very long time, that was the entire inventory of the universe.
And no heavy stuff at all.
Right. There was no oxygen to breathe, no iron to build with, and certainly no carbon.
So if the universe was just floating hydrogen and helium gas, where did the solid carbon that makes up, you and me actually come from? Like, how do you get from a cloud of gas to element number 6?
Well, you need a forge. And the universe provided the most extreme environment imaginable for that. The deep cores of ancient dying stars.
Oh, wow. Okay, setting the stage.
Yeah, as these massive stars lived out their life cycles, their immense gravity pulled everything inward, right? Creating unimaginable heat and pressure. And under those specific conditions, those light hydrogen and helium atoms were literally stripped down and violently smashed together.
So this is nuclear fusion.
Exactly. This process of nuclear fusion forces simple atoms to fuse into heavier, more complex elements. And one of the most critical elements forged in that stellar crucible was carbon.
I want you to hold up your hand right now, just if you're listening, and just look at it. Because when those ancient stars eventually ran out of fuel, they collapsed and exploded in these incredibly violent events called supernovae.
The biggest explosions in the universe.
Yeah, and those explosions scattered all that newly created carbon across the vastness of space. So every single carbon atom inside your body today, the carbon in your heartbeat, your muscles, the neurons firing in your brain to process these words, it was all forged inside a star billions of years ago.
It's incredible. You are quite literally made of stardust.
It's just, it blows my mind every time I think about it.
The atoms animating your body right now are ancient cosmic debris. But, to understand why this specific stardust became the foundation for all life, we have to zoom all the way in.
Right. Getting past the poetry.
Exactly. We need to examine the actual atomic architecture of element number 6.
Okay, so let's put a single carbon atom under the ultimate microscopic lens. What are we actually looking at here?
It's remarkably elegant, actually. Every carbon atom contains 6 protons in its nucleus, and usually 6 neutrons packed in right alongside them.
Okay, 6 and 6.
Yeah. And orbiting that central nucleus, it has 6 electrons. Those electrons are arranged in 2 energy levels, or shells.
Like rings around a planet.
Sort of, yeah. 2 electrons sit in the inner shell, tightly bound to the nucleus, and 4 sit in the outer shell.
See, I was reading through our sources for this deep dive, and I have to say, just having 6 protons and 6 electrons doesn't sound inherently magical. Lots of elements have neat little structures, you know.
Sure they do.
But it struck me that it's not the structure itself, but how that structure behaves. Think of carbon like the ultimate universal multi-tool of the periodic table.
Oh, I like that analogy.
Because the value of a multi-tool isn't just the steel it's made of, right? It's the fact that you can fold it, lock it, and connect it to 100 different things to solve complex problems.
That captures the mechanics perfectly. The multi-tool aspect comes directly from those 4 outer electrons, the valence electron.
The ones on the outside ring.
Right. In chemistry, atoms are constantly trying to reach a state of stability. And for most, that means having a full outer shell of 8 electrons.
Okay, they want E to be happy.
Exactly. But because carbon has exactly 4, it sits right in the middle. It's in this unique chemical Goldilocks zone.
Oh, because it's exactly halfway to 8.
Yes. To reach that magic number of 8, it needs to form 4 stable chemical bonds simultaneously with other atoms.
4 connection points.
Yeah.
Why is that specific number such a game changer? Like, why not 3 or 5?
Because 4 allows for infinite architectural variety. Carbon doesn't just bond with elements like hydrogen, oxygen, nitrogen, and phosphorus. Crucially, it can bond endlessly with other carbon atoms.
Oh, it connects to itself.
Endlessly. It can form long, flexible chains. It can branch out in multiple directions. It can loop into intricate microscopic rings or build massive 3-dimensional molecular networks.
Which brings us to the biological payout, really. Because of those 4 connection points, carbon has an unparalleled chemical versatility. I read scientists estimate it forms millions of different compounds. Millions.
Nothing else comes close. No other element can do that.
Right. And because it can build structures that are incredibly complex and stable, but also flexible enough to change, it became the perfect backbone for the machinery of life.
Yeah.
DNA, RNA, proteins, carbohydrates, fats, enzymes. When you look at them chemically, they are all essentially massive, complex carbon structures.
When you strip a human down to their elemental parts, around 18% of your body by mass is pure carbon.
Wow. 18%.
Yeah. Take DNA, for example. You need a molecular structure that is stable enough to store complex genetic information over a lifetime, but flexible enough to unzip, replicate, and adapt.
Like a zipper.
Exactly. And without carbon's 4 stable bonds providing that scaffolding, the complex chemistry required for living organisms to function and evolve simply falls apart.
It's the dynamic, squishy backbone of biology. But this introduces a massive historical mystery. Because carbon isn't just squishy biology, right?
Far from it.
For thousands of years, ancient civilizations used charcoal for heat and for, cave art. They prized diamonds as these mythical, indestructible gems. Later, they used graphite to write on paper.
Right, and they treated these things as completely different, totally unrelated materials.
Which makes sense. To the naked eye, they share absolutely nothing in common. Charcoal is brittle and porous and black. Diamonds are transparent, perfectly structured, and the hardest natural material on Earth.
And graphite is incredibly soft and slippery.
But then, in the 18th century, scientists finally cracked the code and realized these radically different materials were all the exact same element, pure carbon.
Yep.
I have to admit, this breaks my brain a little bit. How can the softest thing that rubs off on a piece of paper and the hardest thing that can cut through solid rock be the exact same stardust?
Well, it comes down to a core principle of chemistry structure determines function. It is not about what the atoms are. It is entirely about how they connect to each other.
Okay.
We call these different forms allotropes. So if we look at a diamond, we're looking at carbon atoms that were subjected to extreme heat and pressure deep inside the Earth's mantle.
Right.
Under those brutal conditions, every single carbon atom uses its 4 bonds to connect to 4 other carbon atoms in a rigid 3-dimensional tetrahedral grid.
Hold on, let me visualize that.
Mm-hmm.
A tetrahedral grid. So imagine a microscopic 3-dimensional pyramid structure where every single point is locked together in all directions.
Yes. It is an incredibly tight, interlocked network. Because every atom is physically locked in place, unable to move without breaking those immense bonds, diamond becomes the hardest naturally occurring material we know of.
Okay, so that's the diamond. So what is happening inside my pencil? It's the same pure carbon. But instead of that locked 3D pyramid grid, what is the graphite structure doing?
In graphite, the carbon atoms bond in flat two-dimensional layers. They form these hexagonal rings like a microscopic seed of chicken wire or honeycomb,
Oh, so it's flat.
completely flat. And the bonds holding the honeycomb together within that single flat sheet are very strong. But the vertical bonds between the stacked sheets, they're incredibly weak.
Ah, I see where this is going.
Yeah, so when you drag a pencil across paper, those flat layers of carbon literally shear off and slide right over each other, sticking to the page.
Wait, if the same atoms can make a locked diamond in a sliding pencil naturally, what happens if we start actively rearranging them in a lab? Can we build completely new versions of carbon?
We already have, and it is defining the cutting edge of modern materials science. Because think about it. What happens if you take just one single layer of that graphite honeycomb, just one atom thick, peeled away from the rest?
You get a material called graphene.
Exactly.
I've heard graphene called a miracle material.
Yeah.
But help me understand the mechanics here. If I peel off a single layer of graphite from a soft pencil, how does removing material suddenly make it stronger than steel? That seems completely counterintuitive.
It feels like magic, but it's pure geometry. When you isolate that single two-dimensional honeycomb lattice, you are left with unbroken, perfectly distributed chemical bonds.
Okay.
If you apply force to it, that force is instantly distributed across the entire hexagonal network. There are no weak connection points between layers to slip or break.
Wow.
As a result, a single layer of graphene is roughly 200 times stronger than steel by weight.
200 times. That's insane.
Yet it is transparent, flexible, and conducts electricity better than copper.
And if you take that flat sheet of graphene and roll it up into a microscopic cylinder, you get carbon nanotubes, right?
Yes. Unbelievably lightweight, yet insanely strong.
We are talking about the exact same element that makes up the charcoal briquettes in your grill, but simply by rearranging the architecture, it creates materials with world-changing physical properties.
It is the ultimate testament to the multi-tool analogy. It adapts to whatever pressure or technological need arises.
So we've established its atomic structure and these wild physical forms. But carbon doesn't just sit still on a diamond or a lab. It moves. It operates on a planetary scale. And humanity has essentially built our entire modern civilization by tapping into that movement.
Right. We're talking about the carbon cycle. Carbon is constantly in motion in a continuous loop that sustains the Earth.
Where does the loop start?
Well, it's a circle, but let's start in the atmosphere as carbon dioxide gas. Plants, trees, and algae absorb that CO2. They use energy from sunlight in a process called photosynthesis to chemically strip the carbon atom away from the oxygen. They then use those carbon atoms to build sugars, leaves, stems, and wood.
Hold on. Let me make sure I'm really grasping the mechanism here. Are you telling me that a giant, towering redwood tree didn't grow out of the dirt? It built its massive, solid trunk out of invisible gas that it pulled from the air.
That is exactly the mechanism. Trees are essentially solidified air.
That is amazing.
They pull the gaseous carbon in, break it apart, and weave it into solid physical matter using those 4 chemical bonds. Then animals eat the plants, incorporating that solid carbon into their own muscles and tissues.
Predators eat those animals.
Right. And eventually through respiration, just the act of breathing out, or when organisms die and decompose, or when a forest burns, those carbon bonds are broken and the carbon joins back with oxygen to return to the atmosphere as CO2. And the cycle starts all over again.
But there's a crucial missing piece to that cycle, because not all of that carbon immediately goes back into the air, right? Millions of years ago, massive amounts of dead plants and marine life sank to the bottoms of swamps and oceans.
Yes, they were buried under mud and rock.
And over millions of years of geothermal heat and immense pressure, all that trapped carbon didn't decay. It was transformed into fossil fuels: coal, oil, and natural gas.
Think of it as a massive planetary savings account. It is millions of years of stored solar energy locked away in carbon bonds deep underground.
And human civilization basically found that buried savings account and spent it all at once to build the modern world.
Pretty much. Yeah.
Think about your daily routine for a second. We rely on this buried carbon for almost everything. We burn those ancient bonds to release the energy needed to power our cars and generate our electricity. We use the extreme heat of burning coal to forge steel.
We extract carbon compounds from crude oil to manufacture life-saving medicines. The plastics in your kitchen, the rubber for your tires.
Paint, the textiles in your clothes, cosmetics, and the microscopic components in our electronics. We are completely surrounded by and intimately dependent on carbon every single day.
It is the unseen engine of our daily lives. But digging up and burning hundreds of millions of years worth of safely stored carbon in the span of just a couple of centuries has profound consequences for that planetary loop we just discussed.
Right. We can't talk about carbon without talking about the elephant in the room, climate change. So what does this all mean? Let's look at the mechanics impartially based on the sources. What is the actual scientific process happening in the atmosphere?
To understand the mechanics of climate change, you just have to look at how carbon dioxide interacts with light and heat. Naturally, CO2 in the atmosphere acts a bit like a microscopic pinball machine or a one-way mirror.
Okay, a one-way mirror.
When high-energy, short-wave light from the sun hits the Earth, it passes right through the carbon dioxide molecules. It warms the ground. But when the Earth tries to radiate that heat back out into space, it does so as sluggish, low-energy infrared waves.
And those slow waves can't pass back through the mirror.
Precisely. The carbon dioxide molecules absorb those specific infrared waves. The molecules vibrate and then re-radiate that heat in all directions, bouncing a lot of it right back down to the surface.
So this is the greenhouse effect.
Yes. And to be clear, it is essential. Without a base level of CO2 bouncing some heat back, Earth would be a frozen ball of ice, completely incapable of sustaining life.
So CO2 in the air is naturally a vital mechanism for our survival. The problem isn't the element itself, it's the sudden, overwhelming volume.
Right.
By burning massive amounts of coal, oil, and gas, we are taking carbon that was safely buried underground for eons and venting it back into the atmosphere in the blink of a geological eye. We're just adding too many pinballs to the machine.
Yeah, that's a good way to put it. It traps more heat, which fundamentally alters the Earth's average global temperature. Ultimately, understanding carbon, how it cycles, how it stores energy, and how its molecular structure interacts with infrared heat is the key to understanding climate change.
It is a profound paradox. The exact same versatile chemistry that gave us life and allowed us to build an incredible technological civilization is now the central physical mechanism driving our biggest planetary challenge.
It really is.
Well, if carbon is the definitive fingerprint of life, and our own planet's carbon cycle is currently dangerously out of balance, it begs the question, is this cycle unique to Earth? When we look out at the rest of the universe, are we seeing this stardust anywhere else?
Astrobiologists are constantly looking for it. When space agencies like NASA send probes to Mars or point telescopes at the icy plumes of Enceladus or scan the atmospheres of distant exoplanets, they are actively hunting for carbon-based molecules.
So they aren't looking for little green men. They are looking for the structural foundations of biology because of those 4 bonds.
Yes, because carbon's ability to form 4 stable bonds makes it uniquely capable of creating the complex, diverse molecular structures required for life to exist, replicate, and evolve.
It's the only thing that works.
Right. Since every single known living organism relies on carbon-based chemistry, scientists operate on the highly probable assumption that if biology exists somewhere else in the cosmos, it relies on that same elemental multi-tool.
We're looking in the cosmic mirror, basically hoping the stardust that made us made someone else. But bringing it back down to Earth, can the element that caused the problem actually fix the problem? Like, how are we using carbon to secure the future?
The irony is that next-generation carbon technologies are highly likely to be our way out of the climate crisis. Scientists are rapidly developing carbon capture technologies.
Oh, I've seen some headlines about this. How does that actually work mechanically?
Well, imagine massive industrial facilities equipped with gigantic fans that pull in ambient air. They pass that air over specialized liquid solvents or chemical sponges that are designed to chemically bind specifically to carbon dioxide molecules.
Oh, so we catch it.
They literally snap the carbon out of the air, trap it, and pump it deep underground to mineralize into solid rock. We are actively trying to reverse the emissions process.
That's wild.
Yeah.
And beyond just burying it, we're using advanced carbon materials to revolutionize our technology, right?
Yes, absolutely. We are engineering advanced carbon-based batteries that can store renewable energy far more efficiently than current lithium tech. We're using ultralight carbon fiber to build stronger, vastly more fuel-efficient vehicles and spacecraft.
And what about that wonder material we discussed earlier, graphene?
Graphene is poised to replace silicon in our electronics, making our devices exponentially faster, more durable, and vastly more energy efficient.
It is wild to think about. The very element that created life, fueled our industrial rise, and drove our climate struggles is the exact same element providing the chemical solutions to protect our future.
It always returns to the superpower of those 4 valence electrons. Carbon adapts to whatever biological, geological, or technological need arises.
Let's bring everything full circle for you listening. Today, we've gone on a journey from the violent, explosive deaths of ancient stars to the soft graphite sliding out of your pencil.
Quite the trip.
We've seen how carbon is hiding inside your heartbeat, inside every breath you take, every massive forest you walk through, and inside every memory you have structurally stored in the DNA of your brain cells.
It is the chemical foundation of all known life.
The hidden engine of modern civilization and the architecture of tomorrow's technology.
I always come back to the sheer poetic symmetry of it all.
What do you mean?
Well, the simple, everyday act of holding a pencil or looking at a diamond or just taking a deep breath, it physically connects you directly to stars that died in the deep cosmos billions of years before the Earth even existed.
Stardust in our veins, literally.
Literally.
But I want to leave you with one final provocative thought to mull over on your own today. We've established that carbon's unique superpower, its ability to form 4 stable bonds, makes it the singular, undisputed foundation for all known life on Earth.
Right.
But look at the periodic table. Just below carbon, sitting right there in the exact same column, is another element that also has 4 valence electrons. Silicon.
Oh, that's an interesting point.
It shares that exact same structural ability to form 4 bonds and build massive complex chains. So if we are made of carbon stardust, could there be another element hiding in plain sight, like silicon, serving as the chemical backbone for life on a completely alien, unimaginable world?
It really makes you wonder.
Could we be searching the stars for carbon when we should be looking for something else entirely? Thank you so much for joining us on this deep dive. Keep questioning the universe around you.